People talk about quantum computers as if they are a form of magic, so let's see what all the fuss is about. And while you're here, please like, comment, rewatch, share and subscribe. The myth suggests that these machines will arrive suddenly, solving all of humanity's problems overnight, rendering our current technology instantly obsolete. The reality, however, is much slower, more methodical, ultimately more interesting. Quantum computers are not a replacement for the classical computers that power our world. They are a new kind of specialized tool, designed to solve a specific class of problems that are currently intractable. They may indeed change some things in profound ways, but they will not change all things at once. The journey from laboratory curiosity to industrial game-changer is a long and challenging one, paved with incremental breakthroughs rather than a single dramatic leap. This video will give you the clear facts, separating the genuine potential from the breathless hype. We will explore what makes a quantum computer so different from the device you are using right now. We will look at what a classical computer does with its simple, binary logic, and contrast it with the strange and powerful world of the qubit. The core of this technology is not magic, but a deeper, more complex set of rules derived from the laws of quantum mechanics. Understanding these fundamentals is the first step toward appreciating the incredible promise and the formidable challenges ahead. The goal here is not to overwhelm you with complex mathematics or physics, but to offer a plain and curious look at the state of play in computing. We will examine where quantum computers could offer an exponential speedup, as well as the very real limits scientists are grappling with today. To understand the quantum revolution, we must first appreciate the elegant simplicity of the classical computer. Every application, every website, every digital file is built upon bits. A bit is the most basic unit of information, a simple switch that is either off, 0, or on, 1. All the complex operations, email to video rendering, are sequences manipulating billions of ones and zeros, following clear deterministic rules. A quantum computer uses the quantum bit, or qubit, which is not restricted to just 0 or 1. Thanks to superposition, it can be a combination of both states. Think of a spinning coin. While in the air, it is neither heads nor tails. Only when observed does it resolve into a definite outcome. A qubit behaves similarly until measurement. Qubits can also be entangled, which means linked so that measuring one instantly influences the other, no matter the distance. Einstein called it spooky action at a distance. This interconnectedness creates complex, multi-dimensional spaces. A few entangled qubits represent exponentially more information than the same number of classical bits. For certain problems, quantum machines can explore vast possibilities simultaneously, thus effectively trying many keys at once instead of one by one. This parallelism is not universal. It does not speed up every task. One famous case is factoring large numbers, which is the foundation of much of digital security, and brutally hard for classical computers. Using Shor's algorithm, a quantum computer leverages superposition and entanglement to find factors exponentially faster. This is why experts are developing quantum-resistant encryption now. Despite the promise, building large-scale quantum computers is one of the greatest engineering challenges of our time. The very powers, superposition and entanglement, are incredibly fragile. Tiny temperature changes, stray electromagnetic fields or vibrations can cause decoherence, or noise that injects errors, hence the chandelier-like refrigerators, cooling chips to fractions of a degree above absolute zero to suppress noise. Even then, error correction is essential. Many physical qubits encode one logical qubit to detect and fix errors. Today's devices, tens to a few hundred qubits, are NISQ, noise too high, counts too low to beat classical supercomputers on big, real-world problems. We likely need thousands, perhaps millions of high-quality logical qubits. Bridging that gap is monumental. Progress spans materials, fabrication, control systems, better error correction, and algorithms that exploit today's noisy hardware. Expect early wins in specialized fields, a quantum coprocessor assisting classical supercomputers for parts of molecular simulation and hard optimizations. IBM is a leader in quantum computing due to its consistent hardware development, comprehensive cloud-based access through IBM Quantum Experience, and its widely adopted open-source Qiskit software development kit. Other leading companies include Amazon with its AWS bracket service, IonQ and Rigetti Computing, which use trapped ion and superconducting qubit technologies respectively, and Xanadu, which focuses on photonic quantum computing. We have just touched upon a glimpse of the fascinating world of quantum computing. There's more to come. Thanks for watching. The future is exciting. The future is here.